इंडेक्स तो मैंने बंद कर दिया, अब जैसे ही स्लाइड पे हाँ आ जाएगी, स्मूथ आ जाएगी, स्मूथ आ रही है, चिंता नहीं, मैं गोलाई कर रहा हूँ सर। जैसे ही मैं कर दूंगा मैं आपको ये दे दूंगा, ठीक है, उसके बाद आप ऊपर नीचे वो करते रहिएगा इसी से, तो स्लाइड्स के ऊपर मैं एक्टिव कर दूंगा, ठीक है, सिर्फ स्लाइड दिखाई देगी, आपका चेहरा दिखाई नहीं देगा।
ठीक है। Hello and welcome to the session. In today's session, we will discuss about combinational circuits. What are these? Why we want to discuss about them? And what are the importance of these kinds of things in computer? This particular topic is related to Block 1, Unit 3 of MCS 12. And in addition, in this block, we have referred many textbooks. We have given reference to many textbooks, so you can refer to those textbooks also in addition to this. Right. The basic outline is we will be discussing about logic gates, then we will discuss why we need combinational circuits, then we will go to define introduction to circuit design using a typical technique called Karnaug's map, which we have mentioned as K-map, and then we will be going to drawing the circuits also, like how we can draw those circuits, and then finally we will discuss about one of the most important circuit, that is called an adder circuit, right? So this is what I would like to discuss with you in a short span of around an hour or so. Now let's begin with, let's start with thinking about why we need combinational circuits. Right. So the very first thing which comes to our mind is that when we deal with computer, and when I described in the first session about the computer organization, we also want to discuss how the things are done within the computer. Right. Now, if I want to know how things are done within the computer, then this is the first thing which we need to know, that is the combinational circuit. Right. Now, what do we mean by what is going on? Well, the most basic or elementary level of a computer system is the basic electronics. Now, basic electronics is utilized on semiconductor chips, which most of you may be familiar with the technology, semiconductor technologies. And on semiconductor technologies, what we fabricate is this first basic unit called logic gates. From there, the whole essence of computer starts. In fact, the whole computer is implemented with the help of these simple logic gates, right? Then, logic gates, we will look into the logic gates, but they are very elementary units. So how logic gates then can be converted into better logic, right? Addition of circuits and so on and so forth, that is done with the help of combinational design. Right. So this is where this particular topic, combinational circuit design, plays a very important role, and we would like to study it in more details in that particular sense. So let's look into the basic logic gates first. Now, if you can visualize on the screen, we have very simple statements or very simple things. The first gate which is there is NOT. And what does it do? Very simply, suppose there is an input A. Now, all the inputs in combinational circuits in computer are going to be only binary bits, right? Nothing more than that, right? So this is bits, binary digits only. So it can be either 0 or 1. So the first gate, this will be implemented in electronics, and we don't need to worry about that electronics, because then you need to be an electronic person to deal with that particular situation. So for us, this is what is the basic unit. Okay, so let's look into the NOT gate. What does it do? It simply inverts the value, right? So suppose now truth table is the most important tool to know what a particular function is being done. So suppose the value of A was 0. What this gate will do? It will simply invert this value to 1, that's all. So it is a NOT gate or inversion gate or whatever you call it, right? But it is simply converting the value of A from 0 to 1, or value of A from 1 to 0. So if you input 0, if the value of input is 0, it will be inverted to 1. If the value of A is 1, it will be inverted to 0. As simple as that, right? And the algebraic function is f equals to A prime or f equals to A prime. That sign is missing. Normally we use either the bar or a dash instead of it. That dash probably over here is missing. Okay. The next gate which is there is AND gate. Now AND gate takes two inputs. It is implemented with the help of transistors in electronics, right? This is also implemented with the help of transistors in electronics, and you must have studied in unit 1 itself that large number of transistors, in fact many million number of transistors can be implemented on a single chip today. Very large scale integration and ultra large scale integration. This is what is possible today. So maybe one or two transistors are good enough to implement a NOT gate, and 2 to 3 transistors are good enough to implement an AND gate. So what we see here is A and B. So this is represented as f equals to A and B. There is a dot between, or even if you don't include dot, that's perfectly all right. Okay, and how it functions, just like our AND condition in our programming logic, that if we input 0 and 0, we will get a 0, right? So basically false and false used to give us false. So similarly 0 to 0, 0 and 0, if A and B both are 0, we will get 0. We will get the output as 1 only if A and B both are 1. So this is what is the function over here. Now look into the OR gate. OR gate is once again very simple, the OR logic which you use in your normal programming language. The only difference here is that everything is going to be fabricated within the hardware, right? And for OR gate, what you can see, 0 0 will give us 0, 0 1 will give 1, right? 1 and 0 will give us 1, and 1 1 will also give us 1. So these are the simple gates, 3 simple gates. On these 3 simple gates, 3 or 4 more simple gates can be designed, and the first one is NAND, right? NAND is actually not AND. So this sign over here basically implements inverting the AND gate, right? So you simply invert the AND gate to get f a dot b prime, and what you see here, what we used to get in AND, 0 0 was 0, 0 1 was 0, 0 1 0 was 0, and 1 1 was only 1. Now the whole thing has been inverted, right? So this is what you can see. So all zeros in the output only, right? All zeros in the output have been inverted to 1, and where there was 1, it is inverted to 0. So it is not AND. So inversion of whatever we get from AND input, just invert that output to get NAND. Okay. NOR is similarly inversion of that is OR gate. Okay. So in OR gate we got 3 ones, right, and all those 3 ones have got converted to 0, and for the case of 0 0 we got it 1. So similarly this is what we have is the NOR gate. Now there is a very interesting gate in addition to NOR. Now what happens in NOR, you see, if the inputs are same, then we are getting a 1, right? Okay, whereas in OR what will get, if inputs are same, right, we will get, suppose 1 1 we get a 0, right, in OR, not in NOR, right. Now in this particular case, in case of exclusive OR, when the input is 0 and 0, we will get a 0. When the input is 0 and 1, we get a 1. When 1 and 0, we get an 1. So this is as good as we do in OR. But in exclusive OR, the typicality is if both the inputs are 1, then the output is supposed to be 0. So if one of the input is 1, output will be 1. If all the outputs are same, then the output is going to be 0. So this is a very useful gate, and this is called exclusive OR or XOR gate, and it is used at many different places. That's why we have brought in this particular gate for our discussion. So these are simple logic gates, which can be utilized for further creating complex circuits like adders. How? So let's try to go to that particular domain, and this is through combinational circuits. Now, why do we need to have combinational circuits? They are used to design basic functional units of a computer. Okay, so this is what we would like to see how they are used. Okay, then gates are connected to produce a desired output from its input. Now that is very, very important. But what should be the basis of that interconnection? How gates would be interconnected? How the diagram will be drawn? And it can be expressed by truth table or Boolean function. So whenever we want to design a circuit, the very first thing which we need to do is to design a truth table. And on the basis of that truth table, we can design the Boolean function and we can simplify it with the help of these combinational circuits. Well, there are few design issues also which relates to combinational circuits, and the first one is the depth or the number of gates in a sequence should not exceed a specific level. Reason, the output should be obtained with change in input. Now what happens? Suppose we have a long series of gates. Every gate will introduce slight delay, maybe in nanoseconds, right? Because CPU operates in nanoseconds. But that nanoseconds will accumulate if we have large number of gates connected in sequence, right? So that is what is going to create some kind of delay in the circuit, and we want instantaneous changes. Okay, so that is number one. The second thing is the power constraints, limits due to power constraints, and power constraints is in the form of, like, we cannot output, the terms have been given as fan in and fan out. You can refer to those particular terms. That is number of lines to one gate. If there are large number of lines input to one particular gate, like for AND gate we had 2, right? Whereas for inverter we had only 1 input. Suppose for a gate we have 5, 6, 7 inputs, then that might cause a problem in the power. So 2, 3, that is the in general of 4 is normal, maximum 4 is the fan in normally which we try to create, and fan out is how many outputs, how many further gates this particular gate is going to serve from the output. What we see, we had only one output shown, but that particular output can be fed to many gates further, and this is typically related to the power of the circuit. Right. So that is why we try to restrict these to roughly 2, 3, 4, 2, 3, maybe that is the kind of limit which we would like to keep. Now, how we represent. Now this is very important for you to understand. We are doing some brass tacks before we actually go to the circuit design also. But there is something called sum of product form. Right. Whenever we represent our Boolean function, we represent like Boolean function is also a representation of our circuit. So Boolean function, when we represent, for example, a Boolean function is given over there, f a b c equals to a dash b c dash. C dash over here represents inversion, right? That is not, right? Inversion. And in this particular case, a dot b dash. Now how many variables this function has? A, b and c. Now if a term, this is an expression, total expression, and in that expression we have this as a term, right? So if in this particular term A, B and C all are appearing either in normal form, B is normal, I mean B is simple, but A dash is inverted form, right? So either in this normal form or the inverted form, they should appear. Now this becomes the min term, whereas this is not, because C is not appearing. So this is how we define the min term. Now why we want to worry about min term? Because min term has a typical characteristics, right? And that characteristic is, for example, this particular circuit, if we are designing, and this particular term will obtain a value 1 only when A dash equals to 0, that means A is equal to 0, B equals to 1, and C dash equals to 1, that means C equals to 0. And for all other combination, this particular term will have a value 0. Now this is very, very important, because this is 1:1 match to the truth table. That means one min term will be mapped to exactly one term in the truth table. Now that will lead to many good things when we actually design the circuit. Okay. Now similarly, there is a that is product of some form, which is max term. Now max term is once again in a similar fashion, but in max term everything boils down to 0, right. So this is represented with the help of plus, whereas min term was with the help of ands, right. This is with the help of or. Okay, so this is this is called actually the conjunction and disjunction, but we don't need to worry about those particular terms. That's why we have kept the term simple. Okay, now here if A equals to 0 and B dash equals to 0 and C equals to 0, only then this value will have a value 0. So for max term we will obtain a value 0, not 1 as the case was min term, because min term is and, this is or, so this is where the difference is going to come. And max terms are normally utilized in the same design, design, but then max terms are utilized for some different purpose which we have not explained to a great detail, but you can refer to further readings and go through the utilization of max terms. Okay. Now the combination, once again what we see over here, when A equals to 0, B dash equals to 0, that means B equals to 1 and C equals to 0, this max term will have a value 1. That's all. So these are the two terms which you will be finding in all text. You will find these values. But what is their importance? What I told about min term was very, very important for you, that one min term is equivalent to one entry in a truth table. So we'll see that particular thing. Now let's look into the circuit design, where we will be using K-map. There may be 3-4 methods, but we won't use algebraic simplification. We'll mainly go to Karnaug's map, and Quinn-Maxluski method has been explained in your blog, but that is only for reference purposes, right. And how to use Karnaug's map we will show with the help of examples. So let's begin the problem. So assume that you are asked to design a circuit that accepts 4 bits as input and generate an output 1 if the input is an even number, else produces an output 0. So this is our problem. This normally is not going to be implemented in a circuit design, but just for the sake of explanation we are using it, because we are very much familiar with even and odd numbers, right. So what we want to see, if the input is even, right, even in terms of decimal number, then it should produce an output 1, otherwise it should produce an output 0. So circuit can be designed to do this particular activity also. So let's first draw the truth table for it. Right. So there are 4 inputs. So obviously there are going to be 15 cases for this, 16 cases starting from 0 to 7, that means 8 cases are listed in this place. So is 0 that is even number? No, 1 is also not, but 2 is. So you can see there is a 1 in the output. As soon as the in truth table it becomes 1, it should be an output. Can you see the min terms in this particular case? This is a min term, and this min term is A dash, B dash, C dash, D dash, right. However, in this particular case output is 0. So the min term for the function which we will be using is going to be, function will have the min term A dash, B dash, C and D dash. So this is one min term which will be part of the function. Second min term which will be part of the function is A dash, B, C dash, D dash, like that. Okay. So this is, so 2, 4, now in K-map we don't have to worry about those min terms, right. So 2, 4, 6, they all are having value 1. These are decimal equivalent. Moving to 8, 10, 12, 14, right. So this is what we get. Okay. So this is the truth table. Now this truth table is to be mapped into Karnaug's map. And this Karnaugh map is a graphical way of representing the whole information, right. Now the 4 variables which we had, A, B and C, D, right. So we have 4 variables A, B and C, D. Now what we see, we are representing A, B in this particular axis and C, D on over here. Now notice that what these things represent in both the cases. There is a difference of only 1 bit between the 2 values. For example, from 0, 0 we move to 0, 1. Now technically from here we need to go to 1 0, but 1 0 there is a difference in 2 bits, like this bit is also different and this bit, both the bits are different. So from 0 1 we move to 1 1, and from 1 1 we once again move to 1 0, which is, so all these values are differing in 1 bit only, and cyclic nature of this particular representation, from 1 0 and 0 0 difference is only in 1 bit. Now this has got many advantages, and this advantage will be, when you will be seeing this advantage very clearly when we will be seeing the adjacencies. So now our number equivalents, right, the decimal number equivalent will be 0 0 0 0 is 0, now 0 0 0 1 is 1, and this 0 0 1 0, so 2 is at this particular place, and 3 comes 0 0 1 1 3, so this is decimal equivalent 3. Like that we get 4, 5, 6 and 7, then we get 8, 9, 10 and 11 in the last row. Once again the same logic, you can see 1 0 0 0 is 8, right, so this is how we get 8, 9, you can find out, and 12, 13 and then 15 and 14, that means 14 here and 15 here. Now what we do, we map the truth table. All the min terms are going to be mapped, the ones over here. So what you can see, the first even number was 2, second even number was 4, third was 6, fourth was 12, not 12, 8, 10, 12 and 14, right. So we have mapped all those places where we had 1, we have mapped a 1, remaining all the places we can map 0, but we have not shown that particular 0 in this particular case. If we require some other kind of circuit, f dash, then we will do the max terms, which we are not showing in this particular example. Now the next thing is to minimize, right. So the min terms, all the min terms have been mapped in this particular case, and if we write all these min terms, there are 7 min terms, so the circuit is going to be very, very large. Our objective is to minimize the number of gates, and how you are going to do that? Some min terms will be combined into equivalent term, which is not going to be min term anymore, right, but they need to be combined. Okay, so that, and how we are going to combine those min terms so that we get minimum number of gates in our simplified Boolean function. Now in order to do that, we do adjacency checking, and adjacency checking can be across the this particular case also, that is last column also, last and first column, because what we said, 1 0 and 0 0 both are adjacent to each other in the sense that they differ only in 1 bit. So let's look into the adjacencies for these. The first adjacency which we are listing is shown with the help of all red listing ones. Okay, so you can see one typical adjacency, all ones are adjacent to each other in a column. Okay, so now note one particular thing, whenever you will find 2 of the cells adjacent, then the number of variables will be reducing by 1. If we get 4, then the number of variables will be reducing by 2 in the expression which we will be getting. And if we get 8, suppose there was 1 here, then we would have got adjacency of 8 including all these 4 and all these 4. Suppose we have 1 over there. In that case we will reduce 3 variables. In this case we will be reducing 3 variables. Now how this is represented? Okay, let's see. So what is changing across these? A has changed from 0 to 1. Isn't it? From here to here what we see, A has changed from 0 to 1. Similarly, B has changed from 0 to 1 and 1 to 0. So B has also changed. What has not changed is C across the column and D, right, which happens to be D dash in particular case, right. So our equivalent expression which will come out to be 1, since it is 1, so C, and this is 0, so that means D dash. So all these 4 adjacencies, all these 4 what we say min terms have been combined to like if I see these min terms, it is going to be A dash, B dash, C, D prime. This is going to be A dash, B, C, D prime. So C, D prime will be consistently the same, and all these will turn into 1. So what we will get? the output which we will be going, or the combined circuit for these 4 adjacencies is going to be just CD prime. So you need to read more about it. This is very interesting to find the adjacency and reducing the circuit to very less number of variables, right? Now the second adjacency. So this was the first adjacency which we saw. Now the second adjacency, 4 once again. So first of all, we could have done these 2 ways once only. These 4 ones have already been covered, but we want to find the maximum adjacency, right? So for covering these 2 ones, these 2 are not covered, so we find the adjacency which is the maximum adjacency. That means we have to include these 2, although they are getting included once again. Now let's see what is not changing across them. Okay, so see from here, 0, 0 and 1, 0. So what has changed? C from 0 to 1. So we don't have C in this particular case, but D prime, right? Because 0 has remained 0, so D prime comes into our term. And what we see over in the column side, we have changed. A has not changed, A has remained 1, and B has changed in this particular case. So the determination, so A has not changed and D prime has not changed, so AD prime is the second term which we will get because of this adjacency. Now we have actually covered these 2, all these 4 plus these 2 ones. So the only thing left is this particular one which is still to be covered in our circuit design. Now this one, once again we will use the maximal form to cover this particular one, right? That is why we are taking the adjacent, even for this particular one we are taking an adjacency of 4, so that we get the minimum term. Otherwise for this we would have got A prime, B, C prime, D prime, but with the adjacency we have reduced the number of terms in number of variables in the term. So what you can see here, okay, so what has changed? 0 to 1, that is A has changed, so A will not appear, but B remains 1, so B, okay, and D prime as the case in this particular case. So B, D prime for this particular adjacency. So what is our final circuit? Okay, the final, our expression becomes combination of all these 3. So this was the first, C D prime, then for these 4 that is AD prime, and then for these 4 we get BT prime. So this becomes our simplified circuit which represents 1, 2, 3, 4, 5, 6, 7. Had we used only the min terms, we would have got 7 terms in this particular expression, right? Now we have reduced not only the terms to 3, but also reduced the number of variables also to a great extent. So for finding even number from 0 to 15, we can draw this particular equivalent circuit equivalent to this particular Boolean function, and what we will get? We will get the equivalent circuit. We have not drawn this particular circuit, but we will demonstrate how this particular circuit or similar circuits can be drawn. Let us take another example so that this concept of converting the expression, that is the truth value table, truth table to a particular equivalent function using Karnaug's map can be further explained. Okay, so let's look into problem 2. Once again, this is also slightly hypothetical problem, but let's try to assume that you are asked to design a circuit that accepts 4 bits as input and generates an output 1 if the input is a prime number, else produces an output 0. Once again, for the simplicity we have used prime numbers because we know, but prime numbers will be from 0 to 15 only, and this kind of circuit can be drawn but not necessary, because we can draw different kinds of programs, we can create different programs for prime numbers and even numbers, right? But for the sake of that, how we can do the similar thing using hardware. Okay, now for prime numbers we once again draw the truth table. So prime numbers are 2 and 3, 1 is not a prime number, so we will get 1 here. The prime number is 5 and 7, so you are getting 1s over there. The prime number is, then next prime number is 11 and 13, that's how we get our prime numbers. So this becomes our truth table, and to map this onto K-map for prime numbers, so once again we map them 2, 3, right? Then 5, 7, all right. Then we have 13 and 11. So 11 and 13, so all have been, they have been put into 1. Now this is a slightly disarray kind of a structure. So you will find we will have lesser optimization in this particular case, but still K-map is going to give us some optimization. So let's look into two cases at the same time. So what I was talking about, the adjacency of 2. So these are two different adjacencies of 2 each. So adjacency 1, which is shown with the help of red for 2 and 3, right? There is no further adjacency because what we see only 1 here. There is no 1 here, so it is not adjacent, right? There is an adjacency over here, but that we can cover later on also, right? There is no adjacency of 4. Our first objective is to find the maximal adjacency. Because if there is an adjacency of 8, we will find that. If we are not getting adjacency of 8, then we try adjacency of 4. If we don't get adjacency of 4, then we go to adjacency of 2. Because the more is the adjacency, the more number of bits it will be covering, right? Number 1. Because our objective, one other objective is that we should cover all the bits. It's not that we can leave any of those bits towards the end. So all the bits should be covered in some adjacency. Okay, and this is first objective, and second objective is that we have to find the maximal adjacency as far as possible. Okay, so 1 and 2 in this particular case, what is changing? It's 1 is changing to 0, AB is 0 0 only for both the cases, and C is 1. So the expression becomes A dash because it is 0, B dash, and C because C is this particular thing. As simple as that. And for this green, what we see 0 to 1. So that means A has changed. B is 1. So B will come in its normal form, that is B. Then what has these two have not changed for the column. So B, C dash, and D. So this is what the two adjacencies, what you can see very clearly here. And when we move to the second place, so what these two adjacencies are already covered, these two adjacencies are already covered. So what were left? This and this one were left. So we are covering them with the help of, this is going to be one adjacency of 3 and 7. Because of, I cannot show one particular thing by 2 colors, so I have shown this as 3. So 3 and 7 is one adjacency, and this 3 and 7 is what you can see, A is 0, so A dash, B has changed, so no B, C and D, right? So A dash C D, whereas for this as well as this one, that is 11 and 3 also are adjacent in the rotational way. So what we get here, what has not changed in this particular case, CD has definitely not changed, but what we see here is A has changed and B, so this is going to be B dash CD. So what we see, CD is consistent over here, but B dash is coming out to be in this particular case. Don't think that CD is common and then it is going to create problem. No, it's perfectly all right. Okay, many a times this algebraic simplification can further be reduced in the sense that A dash plus B dash can be put into one bracket and CD can be done, but that we are not going to do because K-map leaves us at this particular simplification only, and this is where we get our final design. That is, we combine all the terms and we get our final function which needs to be drawn, okay, for this particular case. So this is in nutshell what you can do with K-map, right? But how to design the circuits? Okay, now this is the in another example. I think one of the question which was asked to me by one of your student was how K-map can be used with don't care condition. Don't care conditions have been mentioned in your block. So what I did was I created a K-map for prime numbers up to value 9 only. So we leave 11 and 13. So we are designing a circuit which does for single digit decimal number, it tries to find the value of K-map. Now the truth table in that particular case will be drawn up to 9 only, right? The value 9, and 10 is you don't need, and that is where the don't care starts. So for how it's going to be there, so for 2 is a prime number, right? 3 is a prime number, 5 is a prime number, 7 is a prime number, but thereafter, right, so we have drawn 8 and 9 are not prime, but 10, 11, 12, 13, 14 and 15, we don't have to care about these values. Why we don't have to care about these values? Because our circuit is not trying to address them. So in those cases, when your circuit is not trying to address those values, we put an X there. Now remember one particular thing, all ones which we have put, we have to cover, right? We have to cover means some adjacency or some expression, some Boolean term should cover that particular function. But for X, we are not required, we are not required to cover all X, but we should take all those X which help us in reducing the number of gates, right? So we will use those. So for example, these two X and these two ones are very nicely gelling into one adjacency of 4. So we will use them as one particular adjacency, right? In the previous case it was not happening. So now you see, now this becomes one adjacency. As soon as this 4 becomes one adjacency, what has not changed in this particular case? B and D. So BD is, so only term now is BD. So we are able to reduce the terms for the number of variables in the terms further, right? So that is the advantages of using don't care condition. Okay, and finally over here also we have done 1, 1 and XX, and these two X are not covered, we are not bothered about those, right? But all ones are covered, that is what our objective was. So once again, for these two ones and these two X's, what we get? B dash C in this particular case. You can see that is what has not changed is C in this particular case, and over here this for here and here it is B dash. So what we see with the use of don't care condition, it further simplifies the design, right? If we have don't care condition in that particular case, and don't care condition where all the X need not be covered, like we need to cover all the ones when we are dealing with normal circuits without don't care condition. So this was another example. Now how to draw circuit. So what we have covered so far is that we can draw, we can create the Boolean function, but how a Boolean function will be converted to equivalent circuit diagram. So now this is what F equals to A B bar C bar plus A B bar C plus A bar B. Suppose this is my function which is to be drawn, right? So how we draw it? Okay, it simply is that A, B and C, these are the three inputs which we have, A, B and C. A will go through an inversion because that's how A bar will come. B will also go through inversion, right? So gates are used. What gates we are using? NOT, AND OR gate for drawing this particular circuit. So what we get? A, B bar, C, that is what we want. So by inverting we get A bar, by inverting we get B bar, by inverting we get C bar. Now in this particular case, three inputs, A is coming directly, what you can see, A is coming directly to this particular gate, B bar is coming to this particular circuit, and C bar. So inversion and C bar. So output of this gate is going to be A, B bar, C bar. These bars are separate, no combined bar. Okay. In this particular circuit, B bar is coming, okay, A is coming directly, okay, and C is coming straight. So what we get? A, B bar, C in this particular AND gate. A dot B, B bar dot C. So this is how, if we want to draw the circuit for this particular term, we draw it very simply. And then plus means we need to pass them through OR gate. Dots mean we need to pass them through AND gates. Bar means we need to simply invert them. That's it. So this is as simple as this, drawing circuit using AND or NOT gates. Okay, nothing very complex. You can easily do it and enjoy it. But what happens in computers when we are trying to design circuits with the help of semiconductor technology, drawing three different kinds of gate becomes sometimes very cumbersome. So what we need a gate which is functionally complete through which we can draw all the circuits, and one of the combination of those gates is AND or NOT. So if any gate which can draw, which we can use to draw and or not stuff, then that particular gate can be utilized for drawing any kind of circuit. So that is what we mean by functionally complete set of gates. And what we are once again trying to say, those gates which can be utilized. So now only NAND gate, suppose NAND gate is functionally complete set of gates, it can be used to draw and or not, then it can be utilized for drawing any circuit, and only one kind of fabrication will be needed when we are drawing, when we are creating the chips, right? So that is the advantage of functionally complete set of gates, although most of the time we ask you to draw circuit with the help of NOT and OR gate together, because together three of them put together are functionally complete, not one is functionally complete. But can we draw? So let's see whether NAND is functionally complete or not. If something has to be functionally complete, a gate has to be functionally complete, then it should be able to, we should be able to create OR from it, we should be able to create AND from it, and we should be able to create OR from it, and rest NAND, NOR, XOR, all can be created with the help of these gates only. Okay, so let's look into how NAND can be utilized to create NOT. So for as simple as that, you pass A from both the inputs, and what you will get, A NAND A. And for if you can check up the truth table of NAND, in the case of NAND, what was there? For 0 0 we will get 1, right? So if A is 0, this is 0 0, we will get a 1. So inversion. If A is 1, what we will get? 1 1. 1 1 for NAND is going to be 0. So what we are going to get? 0 in this particular case, right? Similarly, for A equals to A plus B. So that is, suppose we are drawing it for A plus B. Then we use something called De Morgan's law, and De Morgan's law I'll explain a little bit later, but De Morgan's law is very, I mean, in fact, if you really want to understand this particular circuit, you need to understand De Morgan's law. And De Morgan's law say that negation of, suppose I am negating A and B, I am negating it, then it is equivalent to A prime, that is A negation, plus B negation. A and B whole negation is equivalent to A negation and B negation. Now in this particular case, if we apply the same logic, that is A prime, that is negation of A and negation of B, whole negation will give us A negation, A prime and negation of that, and B prime negation of that, plus is going to come in between. So A prime becomes A, B prime becomes B. Now this is what you have to see in your material or any of the additional reference material. Okay, so this is what you find over here. Invert it twice, you will get A prime, B prime, and then once again pass through inversion, that is NAND gate, which will give me an expression A prime, B prime, whole prime, which is equivalent to A plus B. So this part you can refer to further reading. Okay, and for the case of XOR, once again, for the case of when you want to represent A and B itself, then what you need to do, pass it through NAND, you get NAND, and then negate that NAND value, you will get the AND value. So this is very, very direct. Okay, so this is the way. Like, what is the purpose? The purpose is very simply that we are trying to create a functionally, see that NAND is functionally complete set of gates, and it can be used to draw any of the circuits. Okay, now I want to draw, now this is a typical example where we have used summation kind of representation for the, instead of truth table, we have used summation, and these are the kinds of questions which are normally asked in your exam, that you are given, suppose there is a function ABC where 1, 2, 3, 4, 5 and 7. So these are the decimal equivalent values, have value 1, and this is summation of that, means only these values will be, that means plus. Okay, so all these values will be having a value 1. Okay, so now if I can map this into a truth table, there is no, I mean, we can directly map this to the K-map rather than mapping it into a truth table. And what you see in this particular case, now we have 3 variables, so we are mapping A, on this side and BC on that side. Now once again you can draw the circuit 0, 1, 2 and 3. You can see the 2 is this side and 3 is on that side. The same logic we are using, 4, 5, 6 and 7. Now 1 is here, 2 is here, right, 2 is here, 3 is here, 4, 5, 7. So 4, 5 and 7. Okay, and then we draw the equivalent circuit. Now if I want to draw the equivalent circuit, first is these 4, right? So first adjacency is these 4, and if I see, so 2 variable will be reduced. So what has not changed between these two? C, right? So this is C. So my function is C plus AB prime, which is going to be, I think AB prime should be this, okay, and A dash prime B, this should be this. So you can you can draw this particular function, but this function we need to draw with the help of, this is an OR gate, right? This is an inversion gate, this is an OR gate, A and B. So we have 1 AND gate, 2 AND gate, 2 OR gates and 2 inverter. So if I want to draw this, but as the functionally complete set of gate is NAND, so we will draw this with the help of NAND. How do we draw with the help of NAND? We create inversion, that is negation of this particular term and negation of that particular term. It's going to be the same. Negation of negation is going to be same. For example, if value A, right, A negation and further negation is going to, A negation is 0. Suppose A is 1, so its negation will be 0, and negation of, once again taking the negation of 0 is going to give us 1. So this logic has been used in this particular case, and what we use, De Morgan's law, as I stated, A plus B whole prime, okay, if this I am representing with the help of negation, equals to A prime, which is negation of A, and B prime. So you can easily see this, the whole thing has been done with the help of this. So we get C prime, A B prime whole prime, A dash B prime whole prime, and there is a negation, still negation overall. This is a typical NAND off. So the overall negation represent NAND off, right? Overall negation, this is negation of all the AND terms, and negation of it is basically NAND. So NAND off, now C prime is simply NAND of C, right? NAND of C basically we can pass through, we can either assume it to be C prime, or just I demonstrated that in both the inputs of NAND gate we will pass C, okay. AB prime is NAND of AB prime, okay, this is NAND of this particular gate, okay, and this A prime B is NAND of this particular A prime B. So this is how you see, that is the NAND is always represented, this is AND, and when we put a prime, this is NAND, right. So this is how you get these values, and now we need to draw, so this function is equivalent to NAND of C, NAND of AB prime, and NAND of A prime B. Now just to simplify, NAND of C is directly taken as C prime, so C prime, and this is like that, B prime and all those things we have drawn directly, and they are passed through A, B prime, we get a NAND, A prime B, that is what NAND of A prime B, so we get the NAND of this. Don't confuse between prime here and bar, both are the same, right? Because like in slide it is very difficult to get a bar, so I am using a prime, but you will find both the convention in different books, right? So this is how, please don't get confused, this means negation only, and prime also means, that is bar also means negation. So finally all the three are passed through another NAND gate to get a function. So if you want to draw logic circuits, so how through NAND gate, then you have to work slightly better, more than that. First, get the function with the help of K-map, okay. So we got the function with the help of K-map, then we took double prime of it, okay, right, and within the prime what we got, different NAND of C, then NAND of AB prime. So basically you can directly see we have to pass this from NAND gates to get the values in that particular sense, right. So NAND of C is C prime, and NAND of AB prime, like that we can get the whole stuff, but only thing is we need to get the NAND of everything in that creation. So this is how you can draw circuit through either AND or NOT gates or only through NAND gates, right? So this is the circuit drawing. So that was the second part. Now let us move on to the third and the final part, and this is adder circuit. Now this is very important for you. I mean, it does not mean the other portion was not important, just understanding of other portion is equally important, but let's look into half adder. And this is the basic circuit which every computer must have. Okay, so half adder is basically, it adds just 2 bits. It does not do anything more than that. Okay, and what truth table for this particular half adder should be? The truth table for this half adder will require just 2 K maps, one each for sum bit and one for carry bit. And how it will, now this is only, there are 2 inputs only, so A and B only, and what you can see that sum bit is 0, 1, 1, 0. Unfortunately, when you draw the K map for this, A on one side, B on another side, there will not be any adjacency, they will be just across. So what you will get? You will get the first term is going to be A prime B and second term is going to be that is A B prime. So that is how you will get A prime B plus A B prime for sum bit. And look into the carry bit. So 0 0 gives us sum bit as 0, out carry bit 0. 0 1 gives us sum bit 1, carry bit 0. 1 0 gives us sum bit as 1, carry bit as 0, and 1 and 1, what does it give us? It gives us a sum bit of 0, 1 plus 1 becomes 2, 2 in 1 0, so sum bit is going to be 0 and carry bit is going to be 1 in that particular case, right? So whenever you want to draw a circuit, first draw the truth table. That is very, very important. Once you draw the truth table, then perform the algebraic, the simplification using K-map. K-map may not be applicable in all the cases, maybe algebraic simplification or so. You actually, this is just an example, we want you to be familiar with this. That is why we are giving you K-map, because it is the simplest of things. Otherwise, there are more techniques like the Quinn-McLucas method and so on and so forth. So you can refer to those if you really are interested in this particular domain and want to go into the circuit designing and other kind of a thing. But circuit designing has moved a lot of steps ahead now, and a lot of programming is done in that. So let's not refer to that particular thing for the time being, but let's go to the half adder once again. And the half adder, what does half adder do? We get a carry bit, we get the sum bit. Okay, now carry bit is simple AND gate, right? So this is how your circuit will look like. So if I'm adding X and Y, if the bits, then AND it will give me some carry, and X, the 2 AND gates for X bar Y and X Y bar, and if I pass through OR gate, it is going to give me the sum bit. You know what you have performed? You have performed addition, a circuit. You have designed a circuit which can perform addition of 2 bits. Alright, it looks good, but in reality there is no addition of 2 bits. In fact, there is another previous carry, like whenever you are adding 2 numbers, there is always a previous carry, right? So when you have previous carry, obviously you will have a different circuit for that. So if I want to do a full adder, right, that is called a full adder, which basically add 3 bits, and the 3 bits are the sum A bit and B bit and carry in bit, that is the previous carry bit, right? So the previous carry, so how it's going to be? So sum bit is going to be in all the 0 0. If the previous carry is 1, sum bit is going to be 1 but no carry. This is 1 and 0, this is all right. In the case of 1 1, it is 0 and 1, sum bit is 0 and the carry bit is 1, right? Once again here no problem, here no problem, the similar way, like 2 bits are being added. Look into this combination, 7th, where 3 bits are added, right? 3 ones are being added. So what we are going to get? 3, which is 1 and 1, right? So carry bit is going to be 1 in this particular case, which is higher, and 1. So this is the only case where we will get 1 and 1 in both the cases as sum and carry. Now the next step, in the previous case we did not draw the K-map because it was too simple. In this case we draw the K-map. Okay, and what we get for the sum bits, we have got a typical mosaic where we cannot find any adjacency, right? So each min term, you can see each term which is appearing over here is the min term in case where the value is 1, right? So for example, ABC is going to be this particular one where A is 1, B is 1 and C is 1, right? So this is how you map all these min terms to equivalent, that is function, which is some function is this particular, these 4 min terms 1, 2, 3 and 4. Okay, whereas in the case of carry, we are getting 3 adjacencies, right? One adjacency will be for 5 and 7, one adjacency will be for 6 and 7 and another adjacency will be for 3 and 7. So we will get 3 adjacencies and 3 particular term. You can try this particular thing out over there. For example, this is going to be B and C. C happens to be the carry in, right? In this particular case. So C happens to be the carry in, A is one term and C is carry in, right? So you can get, you will find all these terms to be available over there. So you can easily add them, you can easily find the design, okay? And then you draw them. Okay, so that is how your final output is going to be. Okay, now instead of A prime, B prime, we have X bar, Y bar, and in case of in place of carry bit, we have P in this particular circuit. So that is the simple change, because these figures are not physically drawn by for the slides. So that's why this change is definitely there. You can refer to this particular change X, Y, P. So all these are actually AND gates. Inverters we have not drawn just for simplification, right? And plus is the OR gate, OR gate. So you can see there are 4 inputs coming to this particular OR gate, and beyond that we would not like to go through. Okay, and in this particular case we have very simple circuit. So BC, like AB happens to be X and Y, right? And C happens to be P. So this is what you see, and we get a carry bit in this particular thing. So it is very simple to draw the circuit, okay, full adder circuit. But so what we moved on so far, we went on from the gate, we moved to the design of combinational circuits, and then we moved on to the design of like creation of the circuit with the help of AND or NOT, as well as with the help of just NOR gate, which happened to be functionally complete. But now let us move to another full adder, another circuit which is designed with the help of full adder, and that makes the understanding slightly in more details. So this was like only 1 bit is added, but then our numbers are larger, right? So first we started with 1 bits, right? Then we went on to adding 3 bits. So we added 2 bits, half adder, 3 bits, full adder. But now we want to do addition of a, let's say, 4-digit number with another 4-digit. So this particular circuit of full adder, so the full adder circuit which we have drawn over there, now this is drawn with the help of box over here, okay, and what you see here is the modes, alright. So the mode, this is very interesting. What we have, this is an adder as well as subtractor circuit, and this adder and subtractor circuit is going to add A as well as B, that is 1, or it will subtract B from A, that is going to be the second thing. Now look into this particular circuit, there is a carry in into the circuit and there is a carry out, and importantly there is a overflow marker over here. And how the overflow is there? Suppose this bit addition, so carry into the side bit, if the carry into the sign bit and carry out of the sign bit, if both are same, then there is no overflow, right? So if both are either 1 or both are 0, output of XOR gate is going to be 0. But if both are different, either this is 0 or that, one of them is 0, suppose this or this, then the output is going to be 1. So not only this circuit tells us about the addition, but it is giving us the overflow thing also. So can you see, now from full adder we have designed this particular circuit full adder as well as how many full adders? Because we need to add 4 bit numbers, so 4 full adders, right? And how many XOR gates? 4 here and 5th one for determining the overflow condition. And can you see that how smartly it works? When we put C in as 1, so what we have done, look into this, when C in equals to 0 is fine, because in the case of XOR gate, it will be simply like the value will be passing as it is, okay. So the B is passed through the XOR gate, and if the mode, that is C in is 0, so 0 with whatever value it will be simply passing, right. If it is 1, so it will be 1. If it is 0, 0, 0, it is going to be 0. So 0 will be passed. So the number will be passed as it is. The B will be passed as 0, 1, 0, 1, and result will be, that is the sum will come out of here, some bits will come out of this particular case, and carry will keep on moving forward. Okay, now I'll tell you the problem of this circuit also, but carry keep on moving forward. So the next gate will work, then the next gate will work, then the next gate will work, and that way the 4-bit addition will be done, just like we do in normal addition of ours. But think in terms of when C in 1, right? In that particular case, what you will get is the complement value, because if B is 1, right? If the B, so for example, B1 is 1, so 1, 1 becomes, for NOR gate or for XOR gate, it is 0, and for 0, 1 it is 1. So for all these outputs will be complement of this particular number. Okay, so what you can see, it's a 1's complement. Okay, and when we add C in 1, it becomes 2's complement of 1, 0, 1, 0 plus 1. It will make 2's complement. So what we are actually adding is the 2's complement. In turn, what we are getting is A minus B. Because we converted B into 2's complement. We negated the B with the help of 2's complement and added into A. That is equivalent to A minus B. So this is another statement. You need to check it. You need to go through it once again, and this is how you are going to learn about it. Now there is a major drawback of this particular circuit. What? That C in first moves to this particular circuit. This particular circuit cannot perform till this circuit has fired. That means C out of this circuit is available. Similarly, so by the time we will reach to this circuit, this must be performed, this must be performed, and this must be performed. Well, now there are faster adders. If you are interested, they call look ahead carry, right? So those look ahead carry adders are having, they design circuits to determine carry faster than this particular circuit. So there you see, the electronics is a game of really logic. It's a game of logic and designing in a very, very systematic way and being very creative. And there is no limit for it. Okay, this is just one circuit adder subtractor circuit. If you want to know more, you can actually learn a lot of things. There are lots of reference books available on this particular topic, and the three books which we have mentioned in our blogs are really, really useful for this kind of a design. And you may, if you are interested in this, you will really enjoy, you can go through those and you will really enjoy this particular topic if you really are interested in the hardware side of the computer and the hardware design side of the computer. Well, finally, check your progress. Please study and draw the circuits of block 1 unit 3. Do all the check your progress given in those blocks. And there are number of assignments, in fact not number of assignments, there is just one assignment which is available on your website, and you should go through that particular assignment, and I think there will be some question which you can answer through that particular through this particular presentation which I have given to you. Thank you so much, but please remember, practice is the only essence here. Relearning, learning this particular thing is very, very important. This is not a simple concept, but with little effort you will be mastering it and you will be really enjoying this particular concept. Thanks for being